Hi everybody, it's Mrs. Dinkelman, and this is Unit 7, Integration Using Trig Identities. The main goal for this particular section is that we want to manipulate some integrals that have trig in them. They're going to have powers of trig that is going to make it difficult to take the antiderivative of, and so we're going to use these trig identities to kind of algebraically manipulate it, and then possibly use U substitution in some of them. So there are a few trig identities that I want you to remember. Really 5 out of the 6 here, but that 6th one we're going to use with trig substitution, which we'll talk about the next section. So the first 3 are all called Pythagorean identities. And I'll be really honest, I really only memorize the first one, and then I figure out how to do the other 2. So let me tell you what I mean by that in case you want to do that as well. So that first one, sine squared plus cosine squared is 1. The way I remember that is there's a really cheesy pickup line that I heard one time that said, I wish I was sine squared and you were cosine squared because together we would be 1. So if you can remember that, then you have basically the 3 of them memorized. So here's what I do. Again, I have this one memorized. Sine squared plus cosine squared is 1. And then let's just say I want the identity that has tangent in it. So I have to remember that tangent is sine over cosine. So if I just divide everything in here by cosine squared, then I'll get the one that I want. So this becomes tangent squared plus 1 equals secant squared. So that's that second one. Well, let's say instead that I don't want tangent, that I want cotangent. So then, again, I have to remember cotangent is cosine over sine. And so I have to divide everything by sine squared instead this time. So then I get 1 plus cotangent squared equals cosecant squared. And I just do that every time I need the other identity. I just have that sine squared plus cosine squared equals 1 written on my paper. So really, to me, that's only one you have to memorize out of those 3. The next 2 are these half angle identities. Again, in my mind, really similar. One's a plus, one's a minus. And so if I can kind of memorize one and just know which way they go, that's fine. This last one, sine of 2x, again, that's something we're going to need next section. So that's something I don't usually see on the AP exam. Okay, so there are a couple cases here, and I've given some advice on what to do in them. I am not a person who likes to memorize things, so I tend not to have that memorized, meaning if I know that sine has an odd power, then I'm supposed to do this. I just try something and see if it works, and if it doesn't, then I try the other way. So let me show you what I mean here in example 1 so that you know what kind of roadblock you might run into. Before I have that discussion, what I want to just make sure everyone understands is that if I have an integral of something like, let's say, sine cubed, that is not, it's not power rule, and let's talk about why. So some people want to just add 1 to the exponent and divide by the new exponent. And the reason that doesn't work, and remember the way that we're going to check this is that we would take the derivative to double check that we're right, and our derivative should be what's ever here. Well, remember that sine to the 4th really means sine with a 4 on the outside in there. So that's really chain rule. So 4, leave the inside alone. Now it's a 3. There was just a 4 down there anyway. Derivative of the inside's cosine. And you can see that these are not the same. So that's just a really important discussion point to have, because when we run into that, I want you to understand why we have to do a little bit more work. All right, so this first one, I am going to make a purposeful mistake. So if you would like to put your pencil down for just a minute and watch me make this mistake and see what we would run into, that's totally fine. So it seems maybe like we could just take that cosine squared and replace it with what cosine squared is equal to. That doesn't seem too strange to try. And if we do that, this integral now looks like sine cubed times 1 minus sine squared. And if we wanted to simplify that, it might seem like that was something we would do. But what we've run into here is just what I was talking about. There's powers of sine that we don't really know what to do with. We can't just do power rule. So we haven't really helped ourselves out. We've just made more powers of sine rather than having some sines and some cosines. So this is when I would want you to stop and try the other way. Generally, like I said earlier with these, we're going to need to do some sort of u substitution eventually. So let's see what I mean by that. So let's try instead here to solve for sine squared. And that doesn't necessarily seem intuitive because I have 3 sines here. So what we're really going to do is we're going to break this up into sine squared and sine. And we'll replace the sine squared. That's what that breaks into. Okay, so integral, instead of sine squared, let's write sine squared is 1 minus cosine squared. And then there's a sine. And then there's a cosine squared. So at first glance, especially if you haven't done these might not seem any easier than the one I did before, but we're going to go ahead and use u substitution. And the way I know this is going to work is I can have u equal cosine, and then du, the derivative, is going to be negative sine. So that's why it's important to have that one extra sign there hanging out so I can use that in du, or it will cancel in du. So again, cosine. This is also why I had us practice at the beginning of this unit, practice u substitution. So remember, we solve for dx here. All right, so this integral now becomes 1 minus u squared. The sine's hanging out. I know that's going to cancel here in a second. U squared, and the dx becomes du over negative sine. So those signs cancel, just don't let that negative get lost. So I think what we have, if we simplify a little bit, this is a negative. If I distribute the u squared, I'm going to have negative u squared plus u to the 4th du. And so that's negative u cubed over 3 plus u to the 5th over 5 plus c. And those are cosine. So negative cosine cubed over 3 plus cosine to the 5th over 5 plus c. Okay, so now the next case is just kind of the reverse of that. If you feel like you got that under control, feel free to just go ahead and fast forward, but I'm going to go ahead and go through it in case you want to practice a little bit. So this time, because the cosine is odd, we're going to leave one little piece of cosine off because that's going to become our du eventually. So let's rewrite here. We're going to have the integral of sine to the 4th. Okay, one of those, so cosine squared, and then a cosine. So the cosine squared is going to become 1 minus sine squared. So this time, u is going to be sine, and the derivative of sine is cosine. Now, I'm going to cheat a little bit. It's not really cheating, but I see cosine x dx right there and cosine x dx right there, so this is just going to become du. We can do that if we can kind of see the obvious substitution there. If you don't see that, go ahead and solve for dx and just make sure that you can cancel every time. But you can see now in BC how we're going to have to do maybe a couple of techniques. It might be nice to be able to skip a few steps. So this is going to be the integral of u to the 4th minus u to the 6th du. So u to the 5th over 5 minus u to the 7th over 7th plus c, and then substitute back in our signs. Okay. So now on example 3 here, again, this is one where, again, it's really important to know that we're not just doing power rule here, that we have to do some sort of trig identity. So this is where the half angles come into place. And this one's going to turn into 1/2. You can actually take that 1/2 to the outside if you want. And this is 1 minus cos 2x. So I kind of like to take that 1/2 out and not worry about it. So the antiderivative of 1, dx, would just be x. And then for cosine, it's sine. Now here's the thing. I don't really want to do u sub again. Sine of 2x, because I had to leave the inside alone. But normally when I take the derivative, it would be multiplied by 2, but there's not a 2 there. So the way I like to think about this is just make sure you divide by the derivative of the inside. That technically only works if the derivative of the inside is a constant. Otherwise, we've created some sort of quotient rule issue for us. Okay, and we can simplify that as needed. Okay, so those are the ones dealing with sines and cosines. Here are some of the ones dealing with tangents and secants. So the first thing, again, because I don't have that necessarily memorized, I have it here, but the first thing I would write on my paper is sine squared plus cosine squared is 1, and then make sure I have this identity. Okay, so with these, again, there is a case here. It tells you if n is even, this is what we should do. But if you make a mistake or if you get to something you're not sure if that's what you were supposed to do, just try it differently. So here's why this one's going to work. So it says to kind of parse this out into 2 secant squareds. So we're going to go tangent to the 4th, and then there's going to be a secant squared. I'll change that here in just a second, and then we'll leave this secant squared alone. So this is going to become tangent squared x plus 1. And the reason this one's going to work is because u is going to be tangent, and then du, derivative of tangent, is secant squared. So I'm going to do that kind of trick again where right there, that's du. So rather than taking the extra step to solve. So we're going to have u to the 4th, u squared plus 1, and then that next thing just becomes du. So we have u to the 6th plus u to the 4th du. Now just kind of a side note as I'm writing these, sometimes there's multiple ways to do these, and you might do it a little bit differently than I did and get a little bit different answer. But as long as mathematically you've done everything right, it's fine. Our answers will be equivalent. We would probably be able to prove that we were equal to each other using some sort of trig identity. But as long as you think you've mathematically done the right thing, you can be fine. Okay, so that's what it looks like to save the secant squared. We save that secant squared because the derivative of tangent is secant squared, so it becomes part of du. And then this last one, this one's a little interesting. So remember the derivative of secant is secant tangent. So in this case, that's what we're going to save off to the side. And again, sometimes you can do them one way or the other and it works out just fine. So let's do what they say here. We're going to have a tangent squared that we're going to use here in a second. There's an extra tangent, and we're going to do secant to the 4th x dx. So this is going to become secant squared minus 1. So we have to be really careful here on this one because the fact that we have secants and our derivative is going to have a secant in it. So u is going to be secant, and then du is secant tangent. So I might, just for the sake of making sure we're doing all this right, go ahead and solve for dx, because I know that might be a little bit of a stretch. If it's not, if you can just kind of take a secant tangent out and cancel them out, that's fine. So trying to think of how I want to make sure I do this one. U squared minus 1. What I kind of want to do is save a secant tangent out here because I know what's happening with my dx. It's becoming a secant tangent in the denominator. So I want those to cancel. What that's going to leave here then, let's see, I had 4 secants. So that's going to be a secant cubed, which would be a u cubed. Okay. Those can be really confusing, so just be really careful and take care of things and let me know if you're having questions with those. Okay, so there's our integral, u to the 6th over 6 minus u to the 4th over 4 plus c, and then back to our secant. So secant 6 over 6 minus secant 4th x over 4 plus c. Just be really careful about that one. I know that one's kind of confusing. Okay, just some random integrals pop up at this point, and I want to make sure that you have them in case I've given you a question where you need them. I have asterisk notes to the 2 that you really should know how to do. I will do one of them and perhaps leave the other one for you to do. So I'll do tangent, and then cotangent should be really similar. So if we rewrite tangent as sine over cosine, to me, the way I say these is anytime the derivative of the bottom is in the top, I know it's a natural log. Let me say that again. Anytime the derivative of the bottom is in the top, I know it's a natural log. I don't like it when that thing rolls around, it makes it go away. So let's do u substitution really quick in case that helps make sense of it. So I'm going to have u equal the bottom. Derivative of cosine is negative sine. So again, if we follow procedure here, we solve for dx, then I have the integral of sine over u, and then I have du over negative sine. I'm just going to rewrite that one more time. Negative on the outside, 1 over u du. So this is negative natural log of u plus c. Well, u was cosine. Well, that's not what this says up here. This says secant. Well, that's because remember that coefficients can pop up and become exponents. So this is the same as natural log of cosine x to the negative 1. Well, written in that way, that means 1 over cosine. 1 over cosine, well, that's secant. So that's how we come up with that one. So that's not one I memorize. I just always take the antiderivative in this way. And if you want to try cotangent, it's the same except for kind of flip-flop there. And you can just make sure that you know what that one is. Okay, go ahead and get going on those trig integrals.